So let's start. I'm going to talk a little bit about HPX today. First, I want to present you a little bit about the bigger picture about the ideas or the problems we are trying to solve and the motivation behind all this. And I'm going to present a general idea about what runtime systems are and what specifically HPX is doing. And I will present some examples and some recent results. The examples will contain code. Okay, the bigger picture. As you all know, probably the amount of transistors in current CPUs or whatever chip, GPU or Intel mic or whatever is increasing tremendously, while the clock speed is separating at some point. So what does it mean? It basically means that the only way that we gain more performance out of the chips is by increasing the parallelity of CPUs and architectures. So this is a picture taken from the top 500 list, which basically shows some development over time, that the amount of processors in the big clusters are increasing over time. So what we have here is, in the lower right corner is a range, are 128,000 processors plus. And yeah, how to deal with those systems and how to deal with the increasing parallelity of our computing environment. One problem we are facing is Amdahl's law. I don't know if everyone here is familiar with it. So Amdahl's law is basically saying if we want to speed up a program with parallel regions, with parallel code, the limiting factor of the speed up is always the serial portion of the code, which is 1 minus the parallel portion of the code, which the parallel portion can be executed by n processors. So what Amdahl's law is saying is that when we have only 90% of parallel code in our application, we are not able to utilize more than 512 processors, because the speedup is saturating at one point. It gets a little bit better at about 95%, but it's pretty bad at 75% or 50%. Unfortunately, Amdahl is not completely right, because we are able to utilize 100,000 cores without problem for some applications. But strong scaling is definitely limited by Amdahl's law. Okay. So what are the impeding factors? So or what makes our application slow? We call it the four horsemen of the apocalypse, and try to coin the term slow, which means starvation, latency, overhead, and waiting for contention. So actually, C would have been here, but W is better for the acronym. So what does it mean? Starvation is when you are not able to utilize the when you don't have sufficient concurrent work to do. Latency is the time distance relay between remote accesses and services. Overheads is the work for management parallel, the parallel critical path, which isn't there in a serial application. And well, contention or waiting for contention is when you have a single resource which multiple threads try to access, and you naturally contend on, for example, network devices, memory controllers, or something like that. And all of these factors impose an upper bound on both weak and strong scaling. So everyone familiar with weak and strong scaling? So for those who are not familiar with those terms, weak scaling is basically you have a problem size, and when you add a processor to your computation, you increase the problem size. So yeah, And strong scaling is you keep the problem size constant and you just add more compute resources to it. Okay, so runtime systems. I hope it's clear from those that we need something to manage the slowness of our applications. So runtime systems. The main runtime system task is to manage parallel execution, which is trying to solve the starvation problem. Managing parallel execution means that we need to expose parallelism and have the runtime to adaptively manage these parallel tasks and resources. We also need to somehow synchronize those parallel tasks, and we need a proper way to schedule and load balance those tasks. Mitigate latencies is, of course, trying to solve the latency problem. A runtime system should try to hide latency wherever possible, and this is usually done by overlapping communication and computation. Also, you need to sometimes avoid latency by having an adaptive locality management. Oops. Reduction of overhead is a very critical topic, and what we need to reduce overheads is, for example, for synchronization, scheduling, load balancing, communication, context switching, memory management, and address translation. The overheads in a parallel application are very critical in order to have an efficient execution of those. And when you have a runtime system, the implementation of the runtime system can efficiently handle those overheads. So, yeah. And of course, the contention resolution is to, again, load balancing and adaptive routing of requests, and also buffering of certain request types to somehow overcome the contention on certain devices. Also, asynchronous tasks help here a lot. Okay, so what's HPX? Here are the main governing principles of HPX. So I just put in the terms what HPX is not. So probably a few of you have heard of what PGAS is. PGAS stands for Partitioned Global Address Space. A global address space is trying to span the address space of a distributed memory machine into one global address space so that you can access memory on a remote locality. However, instead of PGAS, we want to have a active global address space. The problem with PGAS is that the data distribution is pretty much static. What we try with the active global address space is that we can dynamically migrate certain objects. Instead of message passing, we want to do a message-driven approach. Message-driven in a way that you have remote components which all expose certain member functions or actions which you can call remotely. So you drive an object in your global address space by just sending messages to it instead of passing your data around. Instead of global barriers, we want to have lightweight control objects. Instead of static data distribution, we want to have adaptive locality control. And instead of moving data to work, we want to move work to data. And last but not least, we really want to have a fine-grained parallelism of lightweight threads in order to really utilize all of our processes most of the time, instead of the communication sequential processes where you always have to have some kind of lockstep mechanism. So you send something, you compute something, you wait for something, and you have it in a lockstep kind of way. What else is HPX? HPX is a uniform standards-oriented API. We are trying to to comply to the C++ standard wherever possible. Currently, we have around 70% standard C++ O3 code base with some of the exciting C++ 11 features. 20% of the other languages we have is HTML for the documentation, and a little bit of assembly, but that's not a big deal. And of course, we make heavy use of various Boost libraries. The most prominent one is probably Boost ACO and Boost serialization, which we use for marshalling our data. HPX also tries to expose new and unexpected forms of parallelism. So if you're familiar with OpenMP or MPI or whatever, you usually used to, so for example in OpenMP, you usually just put a pragma in front of a for loop or something, then you expect it to be parallelized, but that's not applicable in a general case. What we try to leverage is that the programmer is writing fully asynchronous code which uses hundreds of millions of threads. Additionally, we are trying to provide a unified syntax and semantics for remote and local operations, which somehow eases the programming of a parallel code. That when you write one application which you develop initially for a shared memory system, then there shouldn't be a problem if you wrote it properly, that you can just extend it to run on 100 machines or 1,000 or something like that. And additionally, we try to make concurrency manageable by providing those lightweight local control objects, which is Dataflow objects and future-based synchronization. So future, probably some of you already know futures from the new C++ standard. And I don't know, are electrical engineers in the audience? Ah, so you probably are very much familiar with the whole Dataflow concept. So this is a very natural way of actually describing an algorithm, but I will come to that later, and it's kind of cool. It's very common in the in electrical engineering and hardware design, but it's not so common yet in software design. If you saw Hans's talk yesterday, they have some similar constructs with the flow graph thing. I think it goes in that direction. He's nodding, so probably right. Right. So additionally, HPX provides a very broad range of runtime system services, which you enable to query your state of the parallel computer at any time and do proper action whenever something changes. Additionally, you can query performance counters to introspect the state of your system and to adjust your algorithm to whatever need you have. HPX is designed and developed for systems of any scale. We currently run on x86 processors, both 32 and 64 bits, and I just ported HPX to Android, so I can say here that we also run ARM devices, and we support Linux, Windows, and Android currently. So that means that HPX is able to run on all kinds of devices, ranging from large-scale clusters over desktop computers, ultrabooks, and handheld devices, very small scale. Yeah. Yes. We HPX runs on the mic, yeah. Actually, the mic is kind of perfect architecture for HPX because of its highly parallel nature. So you have 4 cores on them, and every core is 4-way multi-threaded, so that's actually perfect for HPX. And on the mic, what's very costly are context switches, so kernel level context switches, which we really do not do in HPX. So the HPX threads are not operating system threads; they are lightweight user level threads. So you don't pay the cost of doing operating system context switches. What I want to highlight here with that slide is that despite what you read on the web, so HPX is developed with a high performance computing background. However, I believe that HPX is able to leverage parallelism in all kinds of parallelism, all kinds of applications. If you need to parallelize your algorithm, feel free to use HPX. It's not just for high performance computing anymore. HPX is not just implemented just like that we add features that we think that are cool and stuff, but HPX is built on a very sound theoretical foundation, which is called the parallel execution model. The parallel execution model has been developed by Thomas Sterling. So when I talk to some of you guys, no one knows him. So Thomas Sterling is the inventor of the Beowulf cluster. The Beowulf cluster is basically what nowadays runs Google and Amazon and whatnot. Beowulf is essentially, so the idea of Beowulf was that you buy, you see where you are and you draw a circle with a radius of 50 kilometers around you, go to every electronic store you can find in that radius and buy every compute resources you can get. And then stick them together in a network, and then voila, you have a cluster with put a Linux on it, and then you have a cluster. That's the idea. And the geniality of the parallel execution model is that he analyzed what is there in the parallel software world, in the HPC world, and put it together into one execution model and unified it in a way. So we have this very sound theoretical foundation. You can read more about it in various papers on our website. Boost is open source, published under a very, very liberal license, the Boost software license version 1.0. We currently have 3 core developers. I'm one of them. The other 2, Hartmut Kaiser and Bryce Lelbach, live in Louisiana. They work at Louisiana State University at the Center for Computation and Technology. And over time, we had like 30 contributors to the project. In the last 30 days, we have over 170 commits. So I looked at it. I looked at the commits this morning, and at the time where I made the slide, until now, we have another 10 commits or so. So we are very, very active. We are very, very active in improving HPX almost any minute in time. So if you check out the code today and you see a problem, it's likely to be fixed in a few hours. HPX is developed since 2005. We are currently at version 0.8 and are about to release 0.9 in maybe 2 weeks or so. So supercomputing is next week, which tightens up all our resources. But after supercomputing, we will have a new release, 0.9, and we have a 1.0 release by the end of the year. Okay, so let me give you an architectural overview of how HPX looks like. HPX is designed very modular. We have a few components. So in the center, there's the AGAS address translation, which does which manages the address translation between global addresses and local addresses, and also routes the remote accesses via the parcel layer onto any interconnect. And the parcel handler eventually MQs new actions into the action manager, which are eventually picked up by the thread manager, which, when time comes, hopefully soon, which really efficiently is able to manage millions of threads, then which are handled by the thread pool. The lightweight control objects are objects that are there for executing tasks, doing synchronization, enqueuing new tasks, waiting, and stuff like that. What you also see is the performance counter module, which is standing a little bit outside of the picture. That basically means that performance counters are everywhere. So I didn't want to put arrows into any module, but they really can measure anything in the system. You can even extend them to give you performance metrics for your own application. So that's really cool. And yeah. So the API is designed fully asynchronous. So all possibly remote operations are asynchronous by default. That's one design decision we made in order to really force the developer to think asynchronously and to leverage the parallelism that the runtime system provides. We are able to composite asynchronous operations, and we implemented the M3428 proposal, which was done by Microsoft at the I think previous C++ standards meeting, which enables you to compose futures to reactant futures. All operations, of course, do not have to be asynchronously. You also have the option to make synchronous calls, but the advantage here is that a synchronous call does not block your complete application. It just suspends the user level threads that's currently running, and if you have enough other work, then the other work will get executed. Of course, the API is fully move enabled, so that's probably the most exciting feature that of the new C++ 11 standard that we use. So the move enabling has been done, I think, half a year from now. And what we saw when a user calls an action and remote function, we saw that we had tons of copies of data when we scheduled this task, and this really was not very efficient. So we thought about what can we do about that, and Boost Move was just accepted by them, and then we said, hey, let's move adapt the code. And we sat down and move enabled our entire code base, which was a fun thing to do because we discovered a lot of bugs in GCC and Visual Studio Compiler, because at that time none of the standard containers for std-bind or std-function was move enabled, which caused a high amount of copies for us. And well, we just implemented our own bind and our own function. And what we gained from there is that we now have a remotable function, a remotable HPX function, and remotable HPX bind, so we can we can invoke remote operations in a very natural way. You just find a function and send it to another node, and then it will get executed. That's really cool. And just by enabling the code, we were able to improve the performance of some of our codes by 10%. So if you see a performance bottleneck, enable your code. Really, that's totally worth it. Although it will cause you a little bit of pain, but it's totally worth it. We try to stay as close as possible to the C++ standard library. So here's a collection of functionality of the C++ standard library we try to implement where it makes sense according to the standard. So we have we have HPX thread, which is modeled, which is implementing the same interface as std thread. We have mutex, future, async, bind, function, tuple, and also IO streams. So you're not surprised if you're programming with the HPX framework. You will be able to use what you learned from the new standard. So I think that's a pretty cool feature, and it enables programmers to just use our system. So let's see how programming in HPX looks like. Here is probably one of the simplest programs in HPX. So we have to include stuff, of course. Here's the C++ main function, the C main function, which gets called by the C startup stuff. We then do an HPX init, which sets up the runtime system, and HPX init blocks at this point until HPX finalize is called. We also have support for non-blocking initialization and non-blocking stopping. So eventually HPX main will be called, which is executed inside of an HPX thread. So the problem is in a regular operating system thread, you can't use our futures or our synchronization primitives because we make use of thread local storage, and that's just not there in the HPX main, in the C main function. So you somehow have to lift your code into the HPX world. So yeah, this is just a world, and we return HPX finally. So that's it. Let's do it with remote actions. We have this say hello function, which essentially prints out hello HPX World with the locality ID, which is run. So locality is the term in HPX for node or different process the HPX program runs in. We have this say hello function, and we just print out where this function will get executed. We find the HPX action here, so we need to do some extra stuff in order to do the remote function invocation. This macro basically is boilerplate code to enable the marshalling of the functions here. And this defines say hello action. So action is the HPX equivalent to regular C++ functions. You can do everything and anything with actions that you can do with regular C++ functions. So you can have templated actions, you can have polymorphic actions, and everything you've ever dreamed of. In HPX main, we just iterate over all localities we can find currently in the system, and we just apply the action with the locality ID here. And and then everything that's currently connected to the HPX system, more or less, will execute. So actually, what will happen is the output will only be visible on the main locality where the AGAS service runs to. So the string gets marshaled and sent over to the main locality. So you only get the output of one locality. It's a feature. Yeah. Okay. You can also do this with using synchronized remote actions. So it gets a little bit longer. So we leave out say hello here, but we use it in an actions again. We use it as an action again. First, we have to do a std vector, which will hold all our futures. We iterate over the localities again, and we now we use async, which returns a future. We push it back into the vector, and once we're done iterating over it, we just wait on all the futures and wait until everything has been executed. So in this example, HPX finalized, and so HPX finalized in this example, and HPX wait all in this example has essentially the same effect, namely that you wait on everything until everything got executed. Okay, so next example, Fibonacci number sequence. Any one of you have ever thought of parallelizing this naive recursive implementation? Probably not. Actually, so when I give a presentation about HPX, everyone says, "Oh my God, Fibonacci, you're so stupid. You do it recursively. Just use the formula to calculate it." That's not the point here. I just want to show you a way how to do parallelization with a simple example, which everyone is hopefully familiar with. So how to parallelize this? Well, we have the recursion here, and well, why not just execute asynchronous task instead of invoking the recursion synchronously? That's what we do with using futures here. So instead of executing the function directly, we just say HPX async Fibonacci, and then the recursion starts in the background. So we immediately parallelize this simple recursive function. We synchronize again here. Okay. Of course, we can do that remotely as well. So this is a complete local operation. So when you use HPX, so you can use HPX async with regular functions or functors or lambdas or whatever. But this is not really remote. So yeah, you can send a function pointer to a different locality, because then the address of the function might be totally different. So you have to adapt this into a function again, into an action again, and you can execute it remotely with the same interface. The only difference here is that you have to provide a locality ID, here. So in this example, we just executed on the same locality, but you can think of spawning the execution of this Fibonacci sequence over millions of nodes. So that's not a problem. So the only thing that changed from this example to this example is the use of the ID type, so you can execute it remotely. Yeah.
Sorry if you're going to mention it. Is there a way to stop the recursion? So, for example, I'm not going to exploit 1 million of cluster nodes.
In this example here, this is the recursion is stopped by the the recursion formula. But actions are cancelable. So you can actually say that you don't want to execute it anymore. So you just stop it, say, stop it now, and then it goes away. Does this answer your question? I'm actually not really sure.
Okay, let's say you have 8 nodes, 1 million recursions. So how do you say you just utilize 8 nodes and then you are not going to start any more request calls or remote calls?
Yeah, so this function here, HPX find all localities, returns all localities which are currently in your system. You usually don't say, so the idea of HPX is that you program your stuff in a locality unaware manner. So when you design your parallel application, you don't design it for one specific parallel machine. You design it for a general purpose parallel execution unit, which just happens to have different numbers of localities, different numbers of local threads, and stuff like that. So it more or less just works. So and even if you do a recursion which has a million recursive calls, then HPX is able to manage that. So that's not really a problem we thought about it, because we tried to avoid it by saying program locality unaware, and don't care about how much threads you actually spawn, because HPX is able to manage it. Okay. Yeah. You can also program Fibonacci with data flows, which probably is a little bit more natural. So if you see the evolution from the naive implementation over just using futures to using futures with remote actions, you see that the code gets blown in a way, right? So and eventually you really don't want to call get here. You really don't want to explicitly wait on the result. So that's what Dataflow is for. With HPX Dataflow, you're able to construct construct a Dataflow tree dynamically. So if you look at a program and you see all the sequential statements in your code, then it is a kind of data flow, right? So it only feels natural to well express it with a little bit more syntactic sugar or salt or poison. And express this data flow which is there in your recursive, in your sequential application, and just express it dynamically with the HPX data flow. So this is what I did with Fibonacci here. So we need two helper actions, one which is just returning the identity, and one which is doing the addition. So look at the code for the Fibonacci now. So if you want to end the recursion, we just return the ID action here with the argument that's passed into it. And if you want to recurse, we just issue the add action, and as input parameters, we use the result of a recursive call to fib here. Fib doesn't return a regular int now anymore, it returns it returns a data flow based object. I need to hurry now. How does it look like when you execute it? So when you execute it, you get this data flow graph, and what you can see with this graph now is that every action here just is able to ripple through the system, and everything gets executed in parallel very easily, and that's what we want to show here. So enough of the examples, let's get to recent results. First thing I want to show you here is how good is our threading system. So this graph is actually almost a year old now, and when we compare to Qthreads, TBB, and Swarm, everything got new releases, everything probably improved as HPX improved. And what you see here is that the more cores you add to the system, all the more or less competing solutions just drop in performance, while HPX is able to scale in some point. However, HPX is not able to reach the performance of the competing solutions in the range of 0 to 6 processes. But as I said, we improved there, and I just didn't have time to rerun the benchmark. Another thing is we tried to compare HPX to OpenMP. So what we did here is we run a Jacobi stencil, 5-point stencil code, and on a non-uniform sparse matrix, and just compared it to. So this code uses the Dataflow approach, and we compared it to OpenMP, and we run up to 48 cores here, and what we see here is that HPX is able to almost reach the performance of OpenMP. This graph is also a year old now, and I mean, think of it, OpenMP was, yes please?
What is it on the vertical axis?
That's lattice update per second. So lattice update is one update of 1 point in the grid. And the blue line is the theoretical maximum that we can achieve with this kind of code. I don't want to get too deep in that. Just take home that even though OpenMP was optimized for almost 2 decades now, we are able to reach the same performance with HPX here. And HPX is just 7 years old. Another thing that I want to highlight is the scaling improvement an HPX application is able to achieve. So this is an AMR application. AMR stands for adaptive multigrid method. So adaptive multigrid is we have a uniform grid, and then you just take regions where you think that something happens and refine that, and as a result, you get load imbalances on the different grid regions you refine. So MPI is not able to scale with that application, but we are able to show scaling with HPX here. And it also, you're not able to reach the runtime performance compared to MPI just yet. We're just able to improve the scaling, but again, these graphs are also a year and a half old now. But we are able to outperform MPI at some point. So this is a very new graph. The GDC stands for 3D Gyrokinetic Toroidal Code. It's a code used for some cosmology applications. It's an n-body code, and what we did here is just replace MPI statements with equivalent HPX statements, and you can see that HPX is really outperforming MPI here. I would like to acknowledge Hartmut Kaiser, Bryce Lelbach, and Matt Anderson here. As I said, Hartmut Kaiser and Bryce Lelbach are the other 2 core developers, and Matt Anderson is one of the physicists working with HPX at Indiana University, and he also wrote the AMR and GDC codes. Just more information, visit our blog. We have some articles, we have papers online there. Check out our code, write to the mailing list, join us at IRC, and if you go to supercomputing next week or tomorrow, visit us at booth 607. Thanks.
Any questions?
Yep. And let's call it HPX cluster. Does it require all nodes to be homogeneous, or can it cope with asynchronous nodes? Not asynchronous, but let's say 1 gigahertz box and 5 gigahertz box.
Yeah. So actually, in supercomputing, we're showing a demo where you have live visualization of the simulation running on a tablet. On a visualization node with 4 cores and a bigger node with 32 cores. And we will show live visualization of an n-body simulation, which you're able to interact in real time with the tablet and motion.
And does it have some sort of cluster management, so I can take some nodes offline for maintenance work and take an online data back on?
Yes, HPX supports dynamic addition and removal of nodes. For cluster management itself, you don't use HPX, you use something like PBS or Slurm or whatever's out there and used.
Okay, thanks.
You showed the performance results with this AMR application and the difference between MPI and HPX. What do you think are the reasons for this difference? Is this a better load balancing possible with HPX or less overhead, or what is it?
So the reason why we can achieve better scaling with the AMR applications is that we are able to cope with the load imbalances. This algorithm naturally exposes in a better way. So we are able to balance the loads better than MPI codes do. Okay. In a general, this is just a general statement. I know that people are out there doing load balancing stuff with MPI. I'm totally aware of that, but just as a remark, I believe that you can do load balancing in a better and efficient, and more efficient way with HPX. Not only concerning performance, runtime performance, but also concerning coding performance. So you can code it better.
Is HPX compatible with GPU nodes? Or are you planning on implementing that?
We are planning on implementing it, probably by the end of the year as well.
And if you do so, are you also looking on heterogeneous GPU classes, like you don't have all classes with the same, or almost with the same graphics card?
Yes. Yeah, so we are trying to implement OpenCL for our accelerator offloading. Anything else?
Can you show the next performance slide? Yeah, this one. What is the peak at the end of the?
This one?
That's the 128 cores.
This is 128 cores, yes.
And does that mean that performance drops?
No, performance drops a little bit. Yeah.
And also for the non-default cache size, it also drops, but it just started to drop, right?
Yeah, a little bit here.
So what's the reason for this performance drop?
We don't know yet.
One question you said the system is some kind of auditability, auditable. So Would you like to comment a bit on about ability? If you have a large system and a calculation running on several thousand cores, and you say stop now, how long does it take until the system is stopped?
So to be honest, the biggest application we run so far is the simple Hello World application I showed, but we were able to run it on, let me lie, 8,000 cores. It takes it's reasonably fast, about a minute or so.
To run it or to import it?
To terminate it. So abortion is different. You can abort it in whatever latencies your network has, because it just sends an abort message and calls std abort, and the program just crashes.
Last question.
Okay.
What is the deployment requirements for HTC for your infrastructure? Does all nodes need to be in one network? Do you consider them to be in different data centers with slower connections between them?
Actually, you can use different networks. So whatever your network setup is, you can use it. So we are currently also working on getting HPX into the cloud with and so in the cloud you don't necessarily have to have two computers in the same data center. So whatever your network is capable of, you can use. Yeah. Thanks.